Look closely at how this cell colony multiplies. One cell becomes 2, 2 become 4, 4 become 8, and within seconds the growth accelerates so rapidly it completely overtakes our view. That is exponential growth, a pattern that builds by multiplying rather than adding. This split-screen graph shows exactly how that multiplication behaves compared to simple addition. On the left, we have an arithmetic sequence. Adding a constant number creates a steady, predictable set of stairs. But on the right, we have a geometric sequence, like the numbers 3, 6, 12, and 24. Because we are multiplying by a constant factor instead of adding, the curve launches upward like a rocket. Now, what if I asked you to find the 50th number on that steep curve? Finding the next single step is easy enough. You just multiply by 2. But manually calculating 50 consecutive steps by hand is tedious. It takes too much time, and the chance of a calculation error is high. By the end of this video, you will build a custom predictor formula. This tool will allow you to skip the manual counting entirely and instantly pinpoint any specific number in a geometric sequence. To build this, you only need 2 things: a calculator and a basic understanding of exponents. An exponent is simply a small number written above and to the right of a base number, telling you how many times to multiply that base by itself. Mastering this formula allows you to abandon that error-prone manual process, turning a tedious counting task into a precise, instant calculation. Step 1 is verifying the pattern. Take this sequence: 5, 15, 45, 135. To find out exactly how these numbers are growing, we work backward. Take any term and divide it by the preceding number. 15 divided by 5 is 3. 45 divided by 15 is 3. 135 divided by 45 is 3. Because we get the exact same result every time, we have confirmed our constant multiplier. In mathematics, we call this the common ratio, and we represent it with the lowercase letter r. But beware of sequences that look similar at a glance, like 5, 10, 15, 20. If we apply our division test here, 10 divided by 5 is 2, but 15 divided by 10 is 1.5. The ratio breaks immediately. This failing sequence is actually arithmetic. It grows by adding 5 each time, not multiplying. A common beginner mistake is subtracting the terms to look for a difference, rather than dividing them to find a ratio. Dividing adjacent terms is the strict mathematical gatekeeper. If your sequence does not have a constant common ratio r, the predictor formula falls apart. Once you confirm the sequence is geometric, isolate the very first number in the line. Here, our first term is 5. We label this starting position with a lowercase a. Think of a as your anchor. The common ratio needs a specific starting block to multiply against, otherwise the pattern has no origin point. Now we combine our anchor and our ratio into the master template for the predictor formula. It looks like this: Tn equals a multiplied by r raised to the power of n minus 1. By plugging our specific sequence values into this template, we set a to 5 and r to 3. You might be looking at that small exponent, n minus 1, and wondering why it is there. If we want to find the nth term, let's say the 10th position, why don't we just use the power of 10? To understand why, think about how we reach the very first term. Because we are already standing on the anchor point of 5, we require exactly 0 multiplication steps to get there. Any number to the power of 0 is 1, so 5 times 1 leaves us right where we started. To reach the second term in the sequence, we only make 1 multiplication jump. To reach the third term, we make 2 jumps. You are always multiplying 1 less time than the term's physical position in the sequence. The n-1 exponent acts as a necessary calibration. It subtracts 1 to account for the starting anchor, ensuring the formula perfectly aligns with the actual physical steps required. Let's put this into practice with a new scenario. Our goal is to calculate the 8th term of a sequence where the starting anchor is 3 and the common ratio is 2. Start by writing out your blank master template. Next, substitute the known values into the equation. We are looking for the 8th term, so n becomes 8. Our anchor a is 3, and our ratio r is 2. Before doing anything else, simplify the exponent. 8 minus 1 gives us 7. Here is where you must be careful. You must strictly follow the order of operations, often remembered as PEMDAS or BODMAS. This rule dictates that you must calculate exponents before you perform any multiplication. If you ignore the rules and multiply the base numbers first, saying 3 times 2 is 6, and then raising 6 to the power of 7, you will get an incorrect answer. The correct mathematical path is isolating the exponent first. You calculate 2 to the power of 7, which yields 128. Only then do you execute the final multiplication step. Multiply 128 by your anchor of 3, and you get 384. By successfully slotting your variables into the template and strictly adhering to the order of operations, you completely bypass the vulnerabilities of manual counting and arrive at a precise result in seconds. Excellent work! You have now transitioned from manually guessing sequential patterns to operating a scalable, exact mathematical model. This chart shows exactly how flexible your new tool is. On the left, a ratio greater than 1 maps out explosive growth. But on the right, you can see that if your ratio is a fraction between 0 and 1, the exact same formula correctly maps a sequence that decays steadily toward 0. And if your common ratio happens to be a negative number, the formula still holds up. The sequence will just alternate signs with every step, bouncing between positive and negative values. Now it is time for a final challenge. Try building the predictor formula yourself for this decaying sequence. 160, 80, 40, 20. Here is your hint before you start. Your starting anchor is 160, and your common ratio will be a fraction, specifically 1/2. Good luck setting up your equation. Mastering geometric sequences allows you to precisely map the foundational patterns of change governing the real world.